V2s from my earliest years, to give a little bit of a little more introduction to who I am. My father was in the Chemical Warfare Service, World War II, and he was stationed in London. And one of his jobs was to run around with others in jeeps and try to analyze the remains of V2 crashes in '44, because he was a propulsion expert, or at least becoming one. And that was his first experience, and after that he went to JPL and worked on better understanding the V2 propulsion units. He never got involved in the actual rocketry. He moved on to North American and did other things, ended up working in perfume manufacturing, and then finally in smog, and I figured they were all related. But anyway, V2s were a real conversation piece for my dad, and there were open family days at JPL, and we could see the rocket motors, nothing else, not the full vehicles or anything. And I was just fascinated with all of that, and I equated it completely with astronomy. And so I ended up going to college, being an astronomy major, worked at various observatories. But I had one great big question, and that was, where did the physics come from? Why is physics so important in astronomy? And that got me into history. And I trained in history, got my PhD from the University of Leicester on the origins of astrophysics. And then being very interested in contemporary careers of astronomers in my history work, I started taking oral histories. Now, oral history is a formal interview with someone who has done something important, or has experienced something important in life, and they are formal, and they are recorded, they are transcribed, and very close to you here is the American Institute of Physics. I worked for them in the late 70s, while I was also a professor at Central Connecticut State College. And out of there, I got very, very interested in interviewing people at NRL, about Naval Research Lab, about their work in early space science. Trying to figure out who were these people and how did they get interested in it. Those are the things I was interested in, and this is one of the early books that resulted from it. Now, let me make sure I can advance this. No, let's see, let's try something else. Help. It worked before. Oh, maybe that one, yeah. Okay, there we are. Our understanding of the upper atmosphere, of course, has changed quite a bit over time. The book that I wrote just before this one, which was a two-book package for Springer, was on the race to the stratosphere in the 1930s, which was, I likened it to the race to the moon. And a lot of stuff in the book relates to all of the same issues that we had with the Russians, trying to be the first into the stratosphere and then trying to be first on the moon. It's a very interesting kind of historical corollary. But you can see the limits, conceptual limits of the atmosphere as they were depicted in both the popular literature, like Time magazine, and in the more technical literature, like the Science Service one on the right. And during the balloon period, you know, we got up to, manned balloons at least, got up just barely into the 70,000 foot range, enough to, of course, photograph the curvature of the Earth and doing stuff like that. But all of these were the altitude records and the big news about, you know, the ballooning in the stratosphere always dealt with a human-tended flight. And the idea of sending radio radiosondes, or simply balloon automatic balloons, was much quieter, but it evolved just like the manned operations. I was fascinated in my history work. The question in the 1890s was the oxygen line you see in the spectrum of the sun. Was that actually in the sun, or was it in the Earth's atmosphere? Because of course sunlight has to go through the Earth's atmosphere. And Pluvinol here was the first to send a little spectrograph into the high atmosphere in the first decade of the 20th century, and determined that with height the oxygen line actually changed a little bit but didn't disappear. And that meant that the sun had oxygen in it. Now this is before physics. This is before physical insight helped people understand why the certain lines in the spectrum existed. And so Pluvinol's work was very, very helpful and stimulated others to try to raise balloons into the high atmosphere. Charles Greeley Abbott from the Smithsonian was absolutely convinced that the sun varied in energy output, and those variations could cause climate and crop changes on the Earth. And as I say in one of my other publications, he even carried this concept to Congress, saying, please support the Smithsonian and we will help predict your crop futures. This was in the 1930s. And as a result, the Smithsonian's research side did very well, even during I just missed the word, depression, exactly, thank you. Try not to be myself. And this is a balloon sun pyroheliometer that he built, where the sunlight would come in the left and into that triangular dish, and it would simply heat up a thermometer here, and inside there was a rotating drum with photographic paper film on it. And as the thing rose into the atmosphere, the rotating drum underneath the mercury bulb would produce a thermal curve. And when it leveled off, he was able to go high enough. He said, here is the actual energy we get from the sun. And he kept on doing this over time, and he believed that he saw variations. No, he was seeing atmospheric differences. And that went on, of course. He did this work in 1913, and as you might know, he lived to 101, and throughout all of that, he absolutely was sure that the sun was a variable star, and that you could predict crop futures by understanding these periodicities. Of course, he thought he found 33 of them, and so it made everything very complicated. So these are different ways the sun was studied at times. Eric Radner, though, is really the beginning of it. He had multi-balloon flights in the 1930s, where with simple spectrographs, that's a Cornu spectrograph with a simple prism and the light coming in a slit, parallel, collimated, goes through the prism, produces a spectrum. He was the first to be able to penetrate into the ozone layer or get through it, so that you could reveal the ultraviolet spectrum of the sun. And he got down to about 2,900, just barely 2,900 angstroms, where the ozone cutoff, as you know, is about 3,000 angstroms. Now, this was a very important series of works. He worked with other people on his team, were Fatser and others who were doing cosmic ray work, and it was all done with balloons. And he was very much a leading figure in upper atmosphere physics in Germany. and became very interested in extending his observations into space. In 1942, after the first successful flight of a V2 from Peenemünde, when they knew they had something that was, really potentially an extremely effective weapon, they also realized that since the V2 was a ballistic missile, once it was out of fuel, it was completely dependent upon the density and pressure profiles of the upper atmosphere and what it was traveling through. That would, that could alter its trajectory. And they were trying for an accuracy of, less than, I think, 1,000 yards at the time. And they had to be able to calculate these things. And so von Braun and Erich Schapper and Stegmaier and others worked with Regner to help von Braun, who asked them to produce a package that you could fly on a V2 and bring back scientific data about the upper atmosphere. And it was completely for that purpose. Of course, Regner had other interests too, but it was primarily that for which the Nazis funded this operation. And it was a very, very ambitious thing. It was all contained in what was called the Wegener Tonne, the capsule at the top that would replace the warhead. And that capsule would contain registering barometers, thermostat or thermometers, and also his Cornu spectrograph here in a much more sophisticated version. And the idea was actually pretty practical. The V2 would carry the tonne up into the upper atmosphere and then release it at peak altitude. And then it would fall, parachute would come out, and during the fall, it would make all of its recordings slowly. And that was a darn good idea. And of course, one that was not copied. But the big question was, how much of this was actually built? I had one piece of a hint. When I was hired at the Air and Space Museum in 1981, or when I started working in 81 there, I found in the collection a Cornu prism and two matched collimating lenses, and a letter from Ernst Stuhlinger, who worked with von Braun, saying that he found these in the rubble of Peenemünde after it was bombed by the Allies. Okay, so that was the history as he was presenting it. Unfortunately, once I got to the Deutsches Museum and went through Regner's papers, and that's the good reason, you go beyond the published record, you go even beyond testimony, you try to get to the actual documents of the time. I found that Regner had not delivered his Wegener Tonne until much farther into 1944. And it was only by late 44 that they had the tonne, and they were planning a test of the tonne, a vertical test, but with not all the instruments in it, just to see if the whole thing would work. You fly the tonne up with the V2, you let it out from the nose cone, flipping off the nose cone, and let it come down on a parachute just to make sure it works, and then you fill it with all of the instruments. Well, that never happened, because by then the Russians did overrun Peenemünde. And the Wegener Tonne itself, though, you might find this interesting, was not collected by the Russians. They weren't interested in it. The Americans were very interested in it. And they brought it to Aberdeen and promptly lost it. If anybody knows anybody at Aberdeen, You know, they have a museum there. They're very, very conscious of their history. And the record is that the Ravener's instruments were examined by NRL people. But, you know, we don't have them. Such is history. Isn't history fun? Well, you know, there was a lot of fanfare when the V2s came to the United States. The fact that what the V2 represented, I mean, it wasn't that damaging, you know. Freeman Dyson once said, every time he heard the V2 swish and then the crash and everything like that, he said, boy, that's another MiG that they can't build. It was very effective, but not, I mean, it was very expensive, but not very effective. But still, it was so far beyond anything the United States had or Russia, it was a shock. And as you know, the United States put together as many of them as it could, along with von Braun's team, and brought them to the United States. And here is the one on the upper right was on the National Mall. This is a V2 rocket seized by Army Ordnance. That was not the one that ended up at our museum, but still, it was a major, major leap in technology. The question was, how do we use it? How do we learn about it? How do we make it better? But it was also for the Navy, how do we shoot it down? Because it went too fast. No known method of ground-based or airplane-based weaponry could shoot it down. How do we shoot it down? We've got to build something like a rocket that can intercept it. So those were, you know, a lot of the goals that the Army Ordnance people like Holger Toftoy on the left conferred with von Braun and his people. As you know, the von Braun team was moved to after internment, they were moved to Fort Bliss in Texas, so they were close to White Sands, mainly to help put together the some 55 V2s that the Americans brought to the United States. And the goals of the Army: gain experience in the handling of firing of missiles, develop means to conduct research so that you can improve and use command, communications, and control systems. Provide a new vehicle to test new apparatus, and those are typically bomb delivery. Assist in the development of countermeasures, anti-ballistic, and to expedite developmental testing of instrumentation useful to the creation of new missiles. Well, Army Ordnance with Toftoy and some advisors from the Joint Research and Development Board said, you know, we should recruit some scientists to help us in this. And how do we get the scientists interested? Well, let's go to the military labs and find the scientists who might be interested in getting involved with these rockets. Well, what would the motivations for scientists be? Well, in academics, it would be solving the problems of the physical atmosphere, getting to know the upper atmosphere, getting to know near space, the Earth's relationship to space and the sun, so on and so forth. But it turns out those were the identical goals that the military had to better create a new weapon system. Well, to put it all together, the Army got together with the Navy through the Joint Research and Development Board of the Joint Chiefs of Staff. And they started having meetings in January 1946 between scientists from Harvard and places like, you see Rudolf Ladenburg from Princeton, Harlow Shapley from Harvard. You've got Shapley is all through there. And people from the Air Force, Signal Corps, and various ground forces. These people decided that there had to be a panel of scientists and rocketeers who would meet periodically and decide, well, what should we fly on a V2 to study the upper atmosphere and near space? And it was called at first the V2 rocket panel. And Shapley, who was the director at Harvard College Observatory at that time, and Ladenburg looked for people on their staffs who would join. And eventually they all were put together. Out of the Navy side, the Bureau of Aeronautics pointed to the most promising group that it had at the Department of Terrestrial Magnetism right here in town that had developed something called, well, I'm jumping ahead, the proximity fuse. Anyway, this activity involved NRL, APL, Air Force Cambridge Research Lab, Princeton, Colorado, Harvard, Michigan, so on and so forth. A lot of different groups. Well, what would they do? They turned first to the Applied Physics Lab and a man named James Van Allen. Probably heard of him. During the war, Van Allen developed in his group that were called the 5%ers later on after the war. That means that their work was supported by internal funds of APL, up to 5% of APL's budget. Okay? And the big thing about Van Allen was that he led a group that produced the first operational proximity fuse. That means he made a very strong, very light, very effective device that could go on a large cannon projectile and detect the presence of metallic material close by magnetically, and then tell the bomb to blow up. And those proximity fuses greatly improved the efficiency of artillery during World War II. A great success. And there have been a number of different designs, but Van Allen carried it also to the fleet, became quite prominent in this. And of course, the Applied Physics Lab, which grew out of the DTM group after the war, was very much into anti-ballistic missile technologies. So Van Allen, though, his background was in geophysics and to a certain extent cosmic ray work. He was very interested in the distribution of cosmic ray influx on the Earth. And he had been beginning to fly balloons in various parts of the world, trying to solve problems about cosmic rays. And from those people, they formed a group called the 5%ers that would fill the nose cones of V2s with various instrumentation. Van Allen, of course, is on the right. We have people like Howard Tatel, Art Coyne, Lawrence Frazier, S. Fred Singer. Some of you may know these names or known about them. So on and so forth. And then I want to point out Shirley McCullum. She was labeled at various times a secretary, at other times an office manager. But that was just to cover up what she really did. There we go. Was to load the payloads into the nose cones. Some of the correspondence that I found, very informal correspondence, said, we really don't want to make a point that women are on site working on these things. They shouldn't be there. Yeah, right? You know, nothing's changed. Okay. This is a later fascinating experiment where they would put explosive grenades into the missile, and then at when the missile reached the apex, it would shoot these grenades out and they would explode and be observed from the ground with spectroscopic instruments to be able to calibrate their spectroscopic work, because the calibration could be done because they knew what the little particles were made out of from the grenades. So that's just one of the things. But the major project was cosmic ray work, and they built igloos of cosmic ray chambers in various configurations to study intensity and directionality of cosmic rays, which was a lingering problem in cosmic ray physics. You know, the big argument between Michelson and Compton in the 1930s about, you know, cosmic rays, a global flux, or were they a focused flux? Were they charged? What were they? A lot of questions about that. They came in many forms. This is a cosmic ray telescope, and by being a telescope simply indicated that it could determine the directionality of the cosmic rays. By putting cosmic ray detectors in line in various configurations, they could then determine simultaneous records, which would indicate that a cosmic ray had moved through both of the tubes. Also, there was shielding that could provide an indication of the energy distribution of the cosmic rays. Now, how did they do this? This is a rocket, it crashes. The big thing was, and the most important thing to the military, was telemetry. Trying to develop telemetry systems for communications, command, and control. And the telemetry systems primarily provided information on the orientation of the rocket, on the temperature distribution, the pressure, the composition, everything that could not be, let's say, recorded and survive the landing of the missile. Problem is, missiles weren't designed to land softly. You know, there was a problem there. How do you treat it? And there was some information that at the time, this is pre-electronics, heavy electronics, imaging electronics, there was a time when it had to be photographic film and it had to be retrieved. And that is a large part of the middle of the story. Both the APL and the NRL groups, along with the University of Colorado and Princeton, they all tried to make spectrographs that would take sunlight and send it into a spectrograph and photographically record it to determine the nature of the absorbing characteristics of the atmosphere as you moved into space. And what could that be? The parts of the spectrum that became stronger were parts that were absorbed by the Earth's atmosphere, like the ozone bands and things like that. Well, Richard Towsey came up with a very, very intriguing design because, you know, you send a rocket up there and it tosses and tumbles and does all sorts of stuff. And the technology wasn't there yet for what we call pointing controls or stabilizing the rocket. The V2 was not a stable platform. And so what Towsey developed was an ingenious optical system where instead of an open slit, he decided to have sunlight go through a spherical lithium fluoride bead. Now, lithium fluoride, of course, is transparent in the ultraviolet. That's why it was chosen. And they were trying to get as deep into the ultraviolet as possible. And he had two beads on either side of the optical axis of the spectrograph. And whenever the sun was visible to either one of them, it would send sunlight into the spectrograph, and it was a Rowland grating. And that Rowland grating would disperse and focus the light onto photographic film, which ran periodically through an entire roll. So a very, very effective and elegant device that Baird Atomic up in Boston put together. There's the sunlight input. And here is one of the earliest pictures of it being tested inside of the nose cone of the V2. The motor with the sector there would rotate really fast and determine how quickly the device could record spectrum. This is an early photograph from NRL that, of course, was not cataloged, not archived. I found it
in Richard Towsey's collection. I was able to interview Towsey back in the early 1980s. Well, by June 46, they had put together one of these nose cones, and here's someone climbing up there to check it just before launch. Here is launch, and here's the landing. They had to bring in the Army Corps of Engineers to find the remnants of the nose cone. This rocket behaved perfectly. It came back nose first and dug itself into the White Sands Desert. And after digging and digging and digging, Richard Towsey came up with payload bits. And guess what? Even though the film had been wound up into an armor shell of steel that could resist ballistic impact, so to speak, it was never found. So this was the first reality of the space age, is how to bring data back. Certainly the electronic data, that's all fine, but this kind of data was very important. He wasn't the only one who developed these things. Jesse Greenstein, later on a very well-known astronomer, created a high-resolution instrument where he was much more interested in the chemistry of the far ultraviolet sun than he was in the atmosphere. And so his device was a rolling pin that had a single long glass spectra plate there that could take one high-resolution image of the sun during a flight. And they placed that between the fuel tanks. And of course, it was never retrieved either. It was totally destroyed. And Jesse Greenstein said quite clearly, that was it for my career in space. And he went to Mount Wilson and Palomar observatories, continuing on. But Towsey kept going. What do we do? Well, the Army was a bit skeptical, as you can see. Ernest Krause, who was the leader of the division, had a number of meetings where they decided, should we only be sending up stuff that can be telemetered back to the ground? And Krause looked for ways to better survive, increase the chances of survival. The way to do it was to get the spectrograph out of the nose cone, and also to blow up the V2 after, when it was ascending. The Germans suggested that. That was a von Braun suggestion. And once they would do that, the tail section would tumble down, whereas the nose section would ballistically come down very fast. And the tail section would be very irregular, and so it would tumble down, and much slower, and a lot more of it would survive. That was the idea. And so they replaced, or they put the spectrograph into the tail of the V2. And there it is on the left, seen in the tail. That's the one that we have on display. That's one of the V2 spectra that we have on display at the museum. And this first flight in the tail was in October, of 1946. On the upper left, that was what was left of the wing. In other words, survived and didn't go very deep. And they found the armor-clad spectrograph intact. Harold Turner and James Bain were the Army people who were closest to the project. I just have them up there. And it was really, I think, a very synergistic group of people who really wanted to make this work. The Army didn't look at the Navy people as, well, they did in some areas, but not in the science area. That was something they were very interested in. And what came out of this was a series of spectra of the sun from different altitudes, 2 kilometers down to 55. And the dramatic difference in those spectra is the penetration into the ultraviolet. As you can see, the atmospheric cutoff is about 3,000 angstroms. That's very, very deep into the blue. It would appear, well, you wouldn't really want to stare at it because it could hurt you. But beyond that is the far ultraviolet, which gets more and more energetic. And here you can see a lot of absorption bands in the far ultraviolet. The magnesium-2 doublet was found at 2800, just like predicted, because part of this was our predictions and models of the sun correct. And it looked like, to a high degree, at least the linear structure of the spectra, which was predicted, came out to be the fact. So that made physicists very happy. And other properties. Over time, those different spectra revealed the layers of ozone, which can be seen in a double-valued thing, the NRL Direct. And in this early publication, it shows how it compared to the ozone studies from Explorer 2 in the 1935 era. And so this was the first measurement of the distribution of ozone in the upper atmosphere. The key was, this is just one shot. The key was, how do you now monitor it over time and see how it changes? And part of NRL went off to do that. But this was the beginning of that, showing that, yeah, this really works. Also, the black body characteristics of the sun, its deviation from black body, were plotted, and they found moderate agreement with Pettit and Stare. Those were ground-based studies, but then it went much farther into the ultraviolet, of course, than anything else. Now, one of the greatest goals that they published about saying, we really want to get to Lyman alpha, which is at 1200 angstroms, much farther into the ultraviolet. Why did they want to get there? Because it was believed to be the spectral line that excited the upper atmosphere of the Earth and created the ionosphere. Nothing could be more important than being able to predict what the ionosphere is doing. Long-range communications depended upon it. That was a super issue, certainly in World War II. So they couldn't get that far, and they were still trying to look for ways to penetrate the ionosphere, penetrate the atmosphere to get to the Lyman alpha. That was the goal that was finally achieved by an Araby rocket with pointing controls in 1952, but not by NRL, but by the University of Colorado. Have you ever heard of the Ball Corporation? Yeah, well, that was their first success. They were then in the physics department of the University of Colorado, and their big success made them of interest to everybody for stabilized platforms, for balloons, for rockets, and they went off and became Ball Corporation eventually. Anyway, so throughout this time, into the late 40s, other NRL staff like Herbert Friedman got involved, extending to the far ultraviolet with electronic means, early Geiger counters into the far UV and the X-ray, which were just as important, but they could not be as selective as spectra. Still, though, they were indicative, and Friedman could not get as far as Lyman alpha, though he tried. And his flight started in 1949. His detectors, of course, were developed in World War II, and they were used for tons of diagnostic applications. Everything from the efficacy of the skins of destroyer vessels to Project Rain Barrel, if you've ever heard of that. That was the detection of Soviet atomic tests and nuclear tests. And his devices were very simple. They were simply Geiger tubes, where there would be a window that would exclude every part of the light except X-ray or UV, depending upon what you wanted. The light would come in, ionize gas inside of there, and produce an electrical current. And that was Friedman's contribution. He applied this, of course, to a very wide range of applications. Also later in the 40s, photography became much more accessible on V2 rockets because they developed faster photographic films and faster photographic systems like cameras. And Clyde Holliday was the first to produce pictures of the Earth from space that just absolutely wowed everybody. This was the confirmation that we were in space, just like the Hubble Space Telescope today, showing us the way the universe looks, you know, modified a little bit for you know, photographic magician work. Here is what the Earth looks like. And that was a big deal. Of course, V2s were usually not the, you know, most reliable devices. A good number of them blew up. Some decided to take off in whatever direction they wanted. As you know, one of them hit Juarez. We bombed Mexico with the V2. That was it. But the V2 also was used as the first step of really reaching space, up above 200 miles. Here is a V2 with a WAC corporal that was a two-stage system in 1950 that reached 400 kilometers with an instrumentation carried by the corporal. Again, that was a big event. But by then the V2s were running out. But they had done their job because the Navy itself had developed the Viking rocket, which was originally developed as a tactical missile able to hit a V2. That was the first proposal. And I have an early report on the Viking rocket that you can see all of the different classification marks on it. Started as high secret or something, and then it eventually was unclassified by about 1953, 54. And about a dozen or so were used for scientific work, but they just turned out to be very expensive and could fly no higher than Arabes that were built by the Bureau of Aeronautics based upon Van Allen's work, putting together a system, increasing the capability of a WAC corporal to an Arabe and being able to produce a system that could carry a usable payload, you know, 20, 30 pounds into space. I mean, the V2 could carry close to a ton, you know. So that's the legacy of the V2. We got one of them, and there's one at Aberdeen. There's a good number of them on display around, and it's always a surprise. People always look at this and say, boy, it's so banged up and everything. Well, that's the way it was made. It was spot welded, and so you see the surface is all crumpled. When I first came to the museum, this V2 had a short label called First Step into Space. I relabeled it by the 1990s with a more sympathetic director at the time, saying world's first ballistic missile system. And we showed how it was built and, you know, the concentration camp conditions for the people who built it and its effect and things like that. And sort of expanded the story. Yes, it was capable of producing what you think of as space science, but it wasn't built for that purpose. And when the gallery opened, the Washington Post published a essay on the op-ed page saying, "New candor at the Air and Space Museum." So that told us we were on the right direction, although we certainly felt so. And that exhibit, whenever the museum opens again, will be accessible for about another year before we close everything down, and we're revitalizing the museum. As a final point, I should correct my biography. It isn't me anymore. I'm emeritus. I retired last April very happily, and I am performing primarily historical research at this time. But that's the story of the V2. I'm open for questions.
Yeah, I have a question concerning, can you hear me all right?
Speak up.
I'd like to know if there was any traceability from the V2 back to Goddard, Albert Goddard, and the mentor von Braun, I'm sorry, Look at you.
I'm sorry.
I'm sorry too, because I can't speak very
Yeah, that'd be good.
well. I was wondering, can you hear me now? Mm-hmm. I was wondering if there's any traceability of the V2 rocket back to Robert Goddard, and von Braun's mentor was a Russian, I can't remember, who also developed a liquid-fueled rocket that was controllable. So where did the Germans get the ideas from?
Well, von Braun was the V2 the original controllable, supposedly.
Right.
Rocket. Well, the
Goddard was first.
Robert Goddard? Oh, yeah, Robert Goddard, not the Goddard Space Station. Yes, yes. He produced a liquid fuel rocket that he launched many sizes, and they got, I guess the biggest one was about 16 feet tall, and it made it to about 1,400 feet, maybe 2,000 feet in the early 20s. He was supported by the Smithsonian, I can say that, but they did not carry any scientific instruments in it. And his goal, as he said very, very bluntly, was for the public, I want to go to the moon. And so, I mean, he was the visionary. Goddard was. But what he told privately was he told the U.S. Mail Service that he could maybe deliver mail much faster than anybody else. And, you know, there was a lot of these interesting things. Smithsonian and then the Guggenheim Foundation both supported him. But the nature of his rockets, yes, they were liquid fuel. And his were among the first for that design. Is that?
Yeah, I was just wondering how the Germans picked it up. They used Goddard's designs or his papers?
Oh, I see what you mean. Well, the V2 was, the Germans called it the Aggregat 4. And it was the fourth stage in building these missiles, which started in the early 30s. And I am trying to remember the name of the person who was the head of that work, and it escapes me right now, I apologize. But yes, it was a long process of developing larger and larger rockets until they had a ballistic missile that was effective.
Was the V1 part of that program too?
The V1 was built also in the Peenemünde area, but it was built by a different part it was built by the Luftwaffe, whereas the V2 was Army Ordnance, and the V1 was a very, very different.
Pulse, right? Yeah,
Yeah, pulse.
Very simple.
Yeah. Somewhat more effective than the V2, some people said, but it was much easier to shoot down.
I've seen bicycle implementations of that already. People have put it on a bicycle.
Well, it had some effect because the United States copied it.
What do they call that other missile they have?
Oh no, with actually a weapon delivery system. We have one. Is it called the Loon? I'm not sure, but we have one at the Udvar-Hazy Center. Yeah. The question over here?
Yeah, the Germans had a rocket-powered airplane too. I think something 162.
That's right.
It was. Did that lead to the development, or did it have any influence on the development of the V2? Because it's just a bigger rocket engine.
Well, excellent question, but I don't have the answer. I don't know even what kind of fuel it would have used, whether it was solid.
Sulfuric. It was a liquid.
It was liquid.
Yeah. Flame fuming or flaming sulfuric acid. Red stuff.
Yeah, they call it the end stuff and the
red fuming something. Yeah. Yeah. I'm embarrassed because my father probably told me all of that stuff when I was 6 years old. I'm afraid I didn't follow the technology. Mike Neufeld gave a talk on the rocket technology here. Maybe it wasn't to your group, but it was another part of
Engineering colloquium.
the engineering colloquium, yeah. His book on von Braun, The Rocket and the Reich, tells you everything. It's a very, very thoroughly researched book. Very worth it, yeah.
Did any scientific results ever come out of the cosmic ray telescopes flown on rockets, considering the short exposure time?
Nothing major. They certainly verified the Pfotzer maximum, but as far as carrying it farther than that, looking at the primary cosmic rays, there was nothing major. Van Allen at one point said, because he went on doing this when he moved from APL to Iowa and lost support, he kept on doing upper atmospheric research. And he used Deacons and Loki and other small rockets that were lifted by balloon, Project Skyhook, so he could get up to the high altitudes. And what he was doing was what you couldn't do with a V2, was launch them from all over the world and examine the different characteristics of the charged realm up there. He did that. He was looking for currents, charged currents and things like that. And eventually, of course, that led to the belts.
Any other questions? Well, let's thank our speakers.
Absolute pleasure. Thank you for asking.